somewhat similar.
Well, hello everyone. Thank you so much for coming to my first forum talk. My name is Jack van Egmond, and today we're going to talk about my late friend and mentor, John Roncz. And John and I pretty much used to talk every day for the last 6 years or so. And during these conversations, he would often refer to what he called his life mottos. And at some point, I just decided to write them down because I found them to be insightful and to be very humorous also. And some of them are actually helping me in my engineering work and just brighten the day of an aerodynamicist in general. So today, I was thinking it would be a great idea to share the most interesting ones with you. Now, John's wisdom strikes immediately. If John knew that I would be here presenting a presentation about him and calling it How to Think Like John Roncz, he'd strike me with the following warning. He'd say, well, Jack, it's pretty easy to teach someone what you know, but it's almost impossible to teach someone how you think. Now, it's really important to get into the difference here. John understood that the easy thing to do as a teacher is to throw everything you know on a couple slides and you let the audience worry about learning something from that. You let your audience worry about connecting the dots. But the more difficult thing, or maybe almost impossible thing, is to structure your own thinking in a step-by-step process and bring your audience along on a journey on how you think. And that's exactly what we're going to try today. We're going to try and do the almost impossible thing. We're going to not go over what John knew, we're going to go over how he thought. So let's begin. I think a very good starting point will be to tell you how I met John. And I met John very late in his life. He was already very well accomplished at that point. It was almost to the date 7 years ago, because it was right after my third visit to Oshkosh. And John and Mike Moore, who's in the audience, were assembling a team of engineers, and John invited me over to his home in Elkhart, Indiana. So what I thought was a friendly meeting at first quite quickly turned into somewhat of a job interview. And most of you who ever met John understand that he's not the person to ask you the ordinary questions. Here's one question I remember, and it has to do with a couple of birds that we trap inside a big balloon. Now, John said that he would give the signal to these birds to take off at the same time. And then he would ask me, well, these birds will inevitably take off, and at some point, their wings and their heads will reach the top of the balloon, imparting some of their momentum. So, will the balloon take off or not? Well, I won't give you too much time to think about the answer. I wish I could. But what John was after was really to see if I had a fundamental understanding of aerodynamics. And that means that whenever the bird goes up, something else must come down. And that something else here is air. And that's a fundamental action-reaction principle. So whenever the birds are hitting the top of the balloon with their heads, an equivalent momentum is imparted by the air pushing down on the balloon. So the answer to the question is no, the balloon does not take off, it actually stays put. It may tremble a bit, it may shake a bit, but overall the balloon will stay where it's at. And another way to look at this question is to see the balloon with air and birds as a closed system. And from this closed system, no downward momentum can escape. Hence, the balloon does not lift off. Well, I guess I passed the test, and John and I really hit it off from there. And And I think where John and I really hit it off was where I introduced him to modern CFD methods. So you can see on the left, John was still using VS Aero at the time, which handles about 5,000 panels for a small aircraft, while I was working with about 50 million elements for a similarly sized craft. Now, what John was really interested in is in seeing what he thought was happening all this time. He had all this experience with flight testing and wind tunnel tests, but he never really had the tool to visualize that. And that really never changed. Over all these years working together, John and I were always analyzing my CFD work together. Whether it was Windecker aircraft, you see on the top left, Alec Wild's Ascender on the top right, which I'll go into a bit more detail later, whether it was flap design, aileron design, airfoil design, and in the bottom right, you even see a 2D cross-section of a vertical axis wind turbine. So John and I really covered a broad spectrum of aerodynamics, which allowed me to learn a lot from John, really. And now, we cannot talk about John without going into his favorite pet theory. It's called John's porcupine theory. Now, when John would look at an airplane, he would notice the high number of appendages sticking out, and he would call that airplane a porcupine. To John, they were too many and also often placed at the wrong position, causing too much drag, and John would be prompted to say something like, well, at least it's a great device for too much airspeed. And that's like a typical humorous response from John, and I think that is very telling of the way he approached aerodynamics. Most people would look like at an antenna like that and would see an insignificant addition to the airplane. And in terms of weight, in terms of geometry, it is. But in terms of aerodynamics, John would see the actual drag equivalent of that, and that's almost like adding a small vertical tail. And if you think I'm exaggerating, if you don't believe me, here's a simulation I did of a cylinder versus a small red dot on top versus an airfoil 50 times the chord length. Now both simulations are in full 3D, but we're zoomed in on a 2D cross-section. As you can see, the flow over the cylinder is very violent. It affects only a small amount of air, but it affects it by a lot. In contrast, the airfoil affects a lot of air, but it only reduces its energy by a little. Overall, making it so that these two geometries have equal drag. So it's important to keep that in mind whenever we need to add an antenna. Now, our next topic is the wing fuselage junction. And again, John would kind of approach it in this humorous way. He said a wing and a fuselage are married together by force, and it's our job as the aerodynamic engineers to make it into a happy couple. Now, whenever you're designing an airplane, the wing and fuselage will need to come together one way or another. And this lesson recognizes that there are both good ways and bad. And that all has to do with how two surfaces interact. In general, they bring out the worst aspects in one another. One thing that happens is that the local velocities will start to increase, increasing friction per square feet of wetted area. But the second thing that happens is now a certain mass flow of air is assailed from two directions. It doesn't lose friction just from one surface, but now two. So there's really potential for trouble here. And for the Ascender aircraft, the engine is on top, and it allows you for beautiful views, and I recommend all of you to look up some videos of that online, but it does introduce a very similar problem. We now have an interaction between, or junction rather, between the engine cowling and the fuselage. And this is, on the left you see the baseline model that John and I started with. you can notice a very narrow junction. On the right, you see a cross-section of the OML and the airplane in blue of how that junction looks like. And you can see it's very narrow, and the small bit of air is losing energy from two sides. So we have quite a bit of friction for the amount of fresh air. Now, if we simulate this in CFD, we look for the low pressure areas. These are areas of high velocity and high stress on the boundary layer, and we notice that this pressure peak is exactly on that junction. So we have some problem here, but now that we've identified the problem, the solution also comes quite easily. Using a fillet here, we reduce the contact area with the air, so we reduce immediately by doing that the amount of friction. But we can do more. We can also very carefully design that fillet such that its lowest pressure area is changed in its location a little bit. And you can see that here. So on the left is the baseline, on the right is the modified version. And you can notice two things. You can notice the increased radius on the right, but also a lower negative pressure peak. Now, that's great in terms of theory, but will it actually work? Well, this is the Ascender aircraft. We're looking at cruise inboard, and you can see the junction, and the cotton veins are really all over the place. This is before the cowling modification. Some of the veins are even moving upstream, indicating large zones of separation, large turbulence in general. Now, after the cowling modification, you can see all cotton veins really behave exactly as they should. They're all pretty calm and along a streamline that you would expect. Overall, I think this cowling modification is a great success. We've identified a problem. We've basically had a very straightforward solution. We verified it in CFD, and finally it agreed with experiment. But there are also projects where the experiment doesn't agree, and it's pretty interesting to go into what John would do then. Now, one example in my case is that in 2020, I was working with a couple of students at Delft University who have a goal for 1 year to design and build a small car that is as fuel efficient as possible. Now, as you can see, it is quite a small car, and for this type of car, the drag estimation is going to be quite important. The estimation drives the motor selection, and of course, it has a huge impact on the fuel consumption. So I simulated the flow at the highest detail. You can even see the laminar flow upstream transitioning to turbulent flow. Eventually you have a turbulent boundary layer, and all the way at the end you have separation. Now you can also see the wake that is generated by the uncovered front wheels. And in any case, given the amount of detail, I felt really confident about giving these students my prediction. And this prediction was a drag coefficient of 0.19. Now, this is months in advance of the car being built, and after the car had been built, we decided to test it inside of the wind tunnel. And there we found something quite strange. We did not find my prediction of a drag coefficient of 0.19 at all. Rather, we found a 73% increase. We found a drag coefficient of 0.33. So you can imagine these students weren't all that happy with my work anymore. Well, what to do? In particular, we can ask, what would John do? And I was lucky enough at the time to be able to ask him, and I discussed this very issue with him. And John replied something like that, like, don't believe the results of an experiment unless it can be backed up by theory. Now, that's kind of reversing common practice. but it's not as easy as simply saying no. I mean, I could just tell the guys at the wind tunnel, you're wrong, and I'm right. Well, that's not like John. What John meant is, if I stand by my results, if my prediction method is fundamental to me, then it becomes my job to find out what actually happened in the wind tunnel. The burden of evidence is really on me. So I did. I started looking back at the wind tunnel. And we can notice two things from this image alone. One thing is the car is relatively large in size compared to the wind tunnel cross-section. Now the wind tunnel is pretty big, but still relative to the car, it's not that large. And the second thing is, you may notice that the car is bolted, or fastened rather, to a aluminum base plate. And the drag is actually not measured on the car directly, but rather on the combination of the plate and the car. So what to do? Well, the fun thing about CFD is really that you can simulate anything you can imagine. And that includes simulating a wind tunnel inside of the real world. All I needed to do was to make a 3D model of the wind tunnel, as you can see here on the right, including the base plate. So I ran the exact same high definition simulation again, and that gives us a great comparison. Now we can compare what the velocity field looks like in open air versus the velocity field in the wind tunnel. Now note, these are exactly set up the same in CFD, except for the wind tunnel simulation has the constrictions of the wind tunnel size. Now you may notice immediately that, that the wind tunnel has much higher velocity, and this is due to blockage. And this higher velocity increases the drag coefficient on the car considerably. Now the second thing is to investigate the base plate. So up top you see the base plate without the car in CFD, and below you see the base plate with the car present. If we solely focus our attention on the flow around the plate, we notice it's much more disturbed on the bottom whenever the car is present. Not only are the velocities much higher, but also if you look at the trailing edge, we notice some separation on the plate. Now, if we put two issues together, these two issues, we can now get out of CFD the drag coefficient as if the car would be measured in the wind tunnel. And this time we get a drag coefficient of 0.3. Well, that's close enough to the wind tunnel results to me. And I think this is a really great example of how the wind tunnel guys are not necessarily wrong, but it is a question whether their setup was representative of the car in open air. And after all, that's what the students were after. And so we can say now with quite a bit of confidence that our original estimate was probably correct. And again, don't believe the results of an experiment unless it can be backed up by theory. Now we're about halfway through. I think it's time for a short pause in which I'll give you the opportunity to consider the answers to this question. And notice the quotation marks. It's a question by John. What's the fastest way to gain 10 knots on any aircraft? Option A, aerodynamic drag reduction. Option B, a more powerful engine. Or option C, a more efficient propeller. So I'll give you all a couple seconds. Well, is there anyone who would dare to take a guess?
I have a question. How fast is the airplane going? What's the base case speed?
You'll find out it's irrelevant. Len, what do you think?
I think it's D. Put the airplane in a dive.
Len is really on a track here. Sir?
B, add more power. You do that faster than all the computations or other stuff.
Well, we're getting real good answers here. I think every answer will work. Len was really close because actually it is secret answer number D. It's not only a question by John, it's also an answer by John. And the fastest way to gain 10 knots on any aircraft is by simply moving the static port 2 inches. Now, it's not only a joke, I think it's also very insightful. It tells a lot about how John thought about experiments. And he understood that it's very difficult to break down any individual contribution to an aircraft by experiment. And that's why theory was so fundamental to John. That's why he liked it so much. He could really get into a drag breakdown with theory and not by experiment. Now, what John impressed me most by over these years is his ability to look at a big problem and break it down into a number of smaller problems. He would say physics works, and he'd add the exclamation mark. Now, he would also then say, whenever we look at the small problems, they're pretty easy to solve. And when we add together, we've just solved the big problem. Now, I can't think of a better example to showcase that, especially in tribute to John, than design an airfoil together. We're going to use a step-by-step approach, and I'll show you it's really not that difficult. Step 1, round in the front, sharp in the back works every time. And it truly works every time. Once we have this, we're really in clear water. We're safe. We can still improve, definitely, but nothing crazy is going to happen. Now, when we even put this airfoil at some angle of attack, we got an L/D of 74 at Mach 0.5 and Reynolds number 3 million. Pretty interesting. We're not even hitting transonic effects yet, although we're very close. As you can see, the dotted line up top. But notice that we have a relatively steep negative pressure peak, and all you need to know about that is really that the higher the peak is causing stress on the boundary layer and lower L/Ds in general. So what can we do? Well, we simply add some camber, nothing special. We're now already at an L/D of 115. And as you can see, some things have changed. We have now lowered the negative pressure peak, but there are still some things that we can improve. Most notably, these three. First of all, we notice that on the bottom leading edge, it's actually eating away from our lift potential a little bit, so we want to bring that down. Then on the top, even though it's better than before, ideally we'd have the negative pressure coefficient flat as a pancake. We want to spread our stress on the boundary layer as much as we can. And third, as you can see, around 80% chord, or 70-80% chord, we don't have equal pressure. So that means the image might look good here, but whenever we're adding ailerons and we have a gap there, that might cause us some trouble. So this is exactly what we did, these three steps. We leveled off the negative pressure peak. We've brought down the pressure distribution at the bottom leading edge, and we've equalized pressure at the trailing edge. And believe it or not, but this is a pretty good airfoil. We now have an L/D of 163. You might think, and John would call it good maybe, and you might then think what I have thought a lot when working with him. Are we really finished, John? Don't we forget something? Don't we need to do more validation? Don't we need to do one more test? This is really me talking, coming out of the academic world, I think. But John had a really simple and comforting answer. He would say, well, just write down, what's the worst that can happen? What's the best that can happen? Simply divide by 2 and there's your answer. Now that brings me to another quote of John, and this is probably his most used and also his most misunderstood quote. It's not hard to be the best, because no one else even tries. How do we reconcile that with John's humble personality? Doesn't seem like John at all. Well, obviously, it's very hard to be the best at a lot of things. And John knew that. John knew that he couldn't outrun Kipchoge in the marathon or that he could beat Carlsen at chess. But both running and playing chess are always pointing us in the right direction. Whenever you're running, whenever you're training for a marathon, well, there's your heart rate, there's your calories burned, there's your pace improvement. Whenever you're playing chess, we have literally arrows pointing us in how we should have moved and how we should move next time. And that's simply not true for aerodynamic design. It's not very clear how to become really good at it, let alone a master at it. We might ask ourselves, where are our arrows? Well, John partly answers this question by another life lesson. He would say, well, I may not know much, but at least I understand everything I know. And I think this quote is really fundamental to John's thinking and to John's success over the years. Now, what it means is that we can only build on top of what we truly understand. We cannot build new knowledge simply on what we already know. We really need to understand it too. And whenever we're making new theories based on just knowledge and not understanding, we'll get something that John called engineering by mythology. In contrast to solid engineering, engineering by understanding. Now, there are quite a bit of mythologies around in aeronautical engineering. These are three of my favorites, but we only have time to go into one of them, and that's going to be simple sweep theory. To explain the myth, I first should explain the actual myth to you. That's the idea that simple sweep theory says, well, whenever you're sweeping back a wing, the effective flow direction is perpendicular to the leading edge. It's not going down straight, it's perpendicular to the leading edge. That delays transonic effects because whenever you're sweeping back a wing, your normal component will always be smaller than your flight stream component. For example, I put here 30 degrees of sweep. Well, that would decrease your normal component by 13%. So, according to the theory, you might say our effective Mach number is 13% lower. But I don't consider this a real explanation at all. First of all, it raises a very important question. Why exactly are we not considering the streamline or the chord in line with the flight axis? After all, we're moving forward. We're encountering air that has momentum along this direction. That's what we're changing with our wing. And I don't really get a good answer out of single sweep theory why we shouldn't look at this picture instead. But it gets a little bit worse, because if we would consider the perpendicular flow, we might ask, where's that change in momentum coming from? Is it just illusory or is it real? More trouble arises whenever we look at the inboard section. Would we really dare to say that the effective flow piles up in the center line? Or worse, crosses one another along the symmetry plane? What about 90-degree sweep? Will we say flow turns 90 degrees? Well, something's clearly wrong with this picture. And I think that this picture of sweep, simple sweep theory, is not helping anybody. I think it's a clear case of engineering by mythology. Now, the real reason why sweep works is a bit complicated, but I think once you understand it, you will not be able to forget it. And I first want to show you, without a doubt, that flow does not move perpendicular over the leading edge at all. This is a CFD simulation of a 30-degree swept back wing, and we're following a couple streamlines up from the top, and as you can see, they move almost straight back. certainly it is not moving perpendicular. Well, I would like to have an explanation that deals with the real flow rather than perpendicular, effective, or perhaps mythological flow. And it's pretty interesting to look at what sweeping a wing actually does to a wing in terms of geometry. Now, as you can see, we have a rectangular wing on the left and a swept back wing on the right. It's the same wing, and it has the same wing area, but as we sweep back, we kind of reduce the span, and therefore, to keep the same area, we have to increase the chord. You can also see that visually from the red dotted line here, the comparison. The chord along the flight axis is elongated in a swept back wing. This effectively, if we look at an airfoil cross-section, this effectively elongates the wing and reduces its relative thickness. And relative thickness is really important for compressibility buildup and for supersonic effects, transonic effects. On the left, here you see a 14% thick section. It's equal, except for thickness, to the one on the right, a 10% section. This is at 0 degrees angle of attack, Mach number 0.75. And on the left, you see flow goes supersonic, and this will cause a shock wave. While on the right, it all stays below the speed of sound, not causing a shock wave. So a thinner airfoil will have a delayed drag onset. And if we look at this picture, this beautiful picture of a variable swept wing aircraft, ironically almost, we can say that sweeping back a wing works just because the flow is moving down straight and not because it's moving perpendicular. As you can see, the chord at some percent span is much longer on the swept back wing. Now, that's one component of why sweeping back a wing works, but there is another, and that's even more fundamental to sweep. Whenever we're considering the leading edge of a rectangular wing, and we can zoom in on the leading edge, on the stagnation point, and you get a picture similar to what you see on the right. We can then identify blobs of air, and in particular, we're going to look at the green one here. Now, this is high pressure buildup at the leading edge. Where can it go? Really, it can only go downstream. It cannot go to left, for another high pressure blob of air is there, and for the same reason cannot go to the right. It certainly cannot move upstream because air is constantly coming on. So it can only move downstream. When we consider a very similar situation for a swept back wing, we notice something changed. If we consider a similar blob of air right there, we notice most of the air will still go downstream. It can still go downstream, but it also alleviates pressure to the side slightly. So it now has an asymmetry which allows for some span-wise flow along the leading edge. And when we look at that in CFD, this is the rectangular wing, unswept wing. In green, you see span-wise velocity. Well, it's almost completely green. No span-wise velocity here. Maybe at the tip a little bit, that's due to tip vorticity. But in a similar configuration of a swept back wing, 30-degree sweep, we notice at the leading edge there's a red line indicating flow is moving towards the tip. Significant span-wise flow. And what that does is really take some of the compressibility buildup at the leading edge and turn it into span-wise flow rather than flow over the wing. So if we go back to the image we looked earlier, actually if you zoom in on that, you can see the slight tendency of the streamlines to move outboard. And that is basically alleviating pressure at the leading edge. And that means a swept wing will always have lower pressures over the airfoil than a non-swept wing. And that's really fundamental. It has nothing really to do with a transonic regime. It's even true in the subsonic regime. It's true from a geometric level. So now you know the real reason why sweep delays wave drag. First, sweeping back an existing wing will increase the chord length and thereby decreasing its relative thickness, delaying wave drag. But the second more fundamental reason is that sweep simply reduces stagnation pressure and thereby reducing pressures over the airfoil overall. Well, that was quite an elaborate explanation, but I do hope that you take this as a good example of engineering by mythology versus engineering by understanding. They're really two different things. One, you might be able to use one time, but the other is a fundamental basis on which you can build new knowledge. Well, we've come to the end of my presentation, and I'd like to finish with one of my favorite quotes by John. I consider it a life lesson, really. You do the best you can, and you disconnect from the outcome. Now, whenever you're an airplane designer, you can feel the weight of the world on you sometimes. Dozens of people may be affected by whatever you do, sometimes hundreds. But that kind of stress doesn't help anybody. And what you have to do is simply do the absolute best you can within the time frame you're given. And that's enough. And that's comforting. That's realizing you're only a single person. And last but not least, that is exactly how to think like John Roncz. Thank you.